Identity of Indiscernibles! This metaphysical idea is fascinating. It's wrong. It's totally wrong when you think about it. But some brilliant philosophers believed it for some very interesting reasons, and so to explain why it's wrong today, we have to articulate some subtle distinctions and ideas which are central to how we think about material objects. So, by examining the principle, we learn a little bit about metaphysics. So let's get started. The principle of the identity of indiscernibles states that for anything X and for anything Y, if X and Y have exactly the same features, then X just is Y. They are not two different things, but one single thing. In the way that Mark Twain and Samuel Clemens are not two different things, they're one single thing. Or in the way that Brian Warner and Marilyn Manson are not two different people, they're actually one and the same person. We could paraphrase the principle of the identity of indiscernibles by saying this: no two things can be exactly alike in every way. Now, it seems pretty easy to imagine counterexamples to this principle. Why couldn't there be two objects which are exactly alike? Well, part of the answer depends on what we mean by exactly alike. If we have objects that are in two different places, does that mean that they're different in some way? Is an object's location one of its features? And if so, does that mean that objects that are in different locations don't have a certain feature in common, namely their location? Well, that question, and a few others, is part of what we need to investigate in order to see whether this principle is true. So, without further ado, let's take a look at where this principle comes from. Our modern version of the principle begins with 17th century philosopher and shapeshifter Gottfried Wilhelm Leibniz, who, in a correspondence with another philosopher and probable shapeshifter Samuel Clarke, discussed the following.
I infer that there are not in nature two real absolute beings, indiscernible from each other, because if there were, God and nature would act without reason in treating the one otherwise than the other, and that therefore God does not produce two pieces of matter, perfectly equal and alike.
From looking at this quote, we can see what Leibniz's argument for the identity of indiscernibles is. It proceeds as follows. First, if two bits of matter were exactly alike, then there would be no reason for God to place one of them at one location and the other at a different location, since the same facts would obtain if their locations were switched. But God never acts without reason, so no two bits of matter can be exactly alike. Now, as soon as we look at this argument, it becomes pretty obvious what the initial problem is. It presupposes a very specific, very contentious theology, the evidence for which is dubious at best. Why should we think that there's the sort of God that Leibniz believes in, which has a very specific reason for every fact in the universe? Indeed, why should we think that there's a God at all? Thus, Leibniz's argument rests on ideas for which we have little antecedent justification. But that's not the worst of it. To see the worst of it, let's turn to... So the identity of indiscernibles says that no two things can be exactly alike in every way. In response, let's consider three counterexamples. First, imagine two electrons. They are as alike can be. Both share the same mass, the same unit negative charge, the same physical dispositions, and so forth. They would appear to show that the identity of indiscernibles is false. Secondly, imagine a universe where history repeats itself over and over, proceeding in epicycles, which begin with a big bang and which end by contracting into a big crunch. Surely two of these epicycles could be exactly alike, and that too would falsify the identity of indiscernibles. Finally, and most famously, consider a case proposed by 20th century philosopher Max Black, who asked readers to imagine a universe which contains nothing but two perfect spheres, each made of chemically pure iron, each 1 mile in diameter, each as alike as can be. The possibility of such a universe would falsify the identity of indiscernibles, and, over the last few decades, it has received a great deal of commentary and discussion. Today, that example is known as Black's balls. Now, because the responses to Black's balls generalize to the other two counterexamples, we'll focus on them for now. There are two basic sorts of responses to Black's balls. One of them incorporates realism about space-time points into the identity of indiscernibles, and the other one involves claiming that there are not two spheres, but rather one single sphere. Let's take a look at each of them. According to the first response, the two spheres in the case of Black's balls do not have exactly the same features, since one of them has the feature of being at a certain point in space-time, namely point P, and the other has the feature of being at a different point in space-time, call it point Q. This is supposed to be a real difference and not just stipulation, because the points P and Q are real themselves. This response claims that spatial points exist and that the spheres differ by their relation to them. Since the spheres differ, they are no counterexample to the identity of indiscernibles, because they're not exactly alike in every way. They differ with respect to their location. A defender of the identity of indiscernibles, who accepted this response, could say that in the case of the electrons too differ by way of their spatial location, and also, in the case of the recurring universe, different epicycles differ from one another, specifically in the order in which they appear. Now, the problem with this response is that it requires there to be a basic difference between two different points in space, even though, by themselves, two different points in space are exactly alike. In other words, if you look at points in space and you believe in those things, it looks like they themselves are a counterexample to the identity of indiscernibles. 2 points in space have no intrinsic features, they're exactly alike, and yet, by stipulation, they have to be different from one another. So this solution appears to undermine itself. Now, there are basically two ways that philosophers have attempted to maintain that there's only one sphere in the example, despite the fact that we seem to be imagining two. The first goes back to 20th century philosopher Ian Hacking, who in 1975 proposed that when we imagine Black's balls, what we're really thinking of is a universe in which space is curved, and so there's one sphere, and it's a certain distance away from itself. There are two basic problems with the response, the first of which is that one should be able to stipulate that space is not curved without begging the question. It seems perfectly conceivable that there should be two iron spheres of the sort that Black describes in a universe where space is not curved. The second problem is that it doesn't work for all counterexamples. If we go back to the case of the electrons, that's not a case where we could just stipulate that space is curved. Our world does not seem to be one in which space is curved around a single electron. Far from it. So that response does not work. The second way that philosophers have attempted to maintain that there is only one sphere in the case of Black's balls was proposed in 1995 by John Hawthorne. He proposes that there's just one sphere, and it happens to be located in two distinct places at the same time. In the same way that, say, we might find the color red in two different locations at the same time, or we might find a certain letter appearing in several different places at the same time on a single sheet of paper, so could we imagine that a single concrete sphere, in this particularly strange circumstance, is in two different places at the same time. Thus, Hawthorne proposes that the sphere may be a bilocated particular. Now, the problem with this response appears when we imagine what would happen if at one of its locations something were to happen to that sphere, and if at the other location the same thing would not happen to that sphere. In other words, suppose that you have the sphere, one sphere, and it's located in two distinct places at the same time. Suppose a bucket of red paint appears above one of those locations and is spilled. Would that mean that both spheres suddenly appear red? Would that mean that the red paint would spill on one sphere, and then red paint would appear at the other location, mysteriously, without any bucket dumping it out? It would just appear there? If you were to kick the sphere at one location, would the sphere at both locations suddenly become dented? How on earth would the sphere at the second location become dented if there were no physical object coming in contact with it, except for at the first location? It seems mysterious, and it seems to amount to a certain action at a distance which we would normally think to be impossible. Well, that seems rather absurd. Since it is absurd, it is implausible to suppose that the one sphere is in two different places at the same time. Okay, so now we've seen that in the face of apparent counterexamples, the defender of the identity of indiscernibles only has two possible responses, and neither of them actually work. The first response, which incorporates realism about space-time points into the identity of indiscernibles, appears to undermine itself because space-time points themselves violate the identity of indiscernibles. The second response, which insists that there is only one sphere in the counterexample, also doesn't work because there are only two ways to try to maintain such a claim. The first involves the question-begging claim that space-time is actually curved around a single sphere in that example, a response which doesn't even work when we consider the case of the electrons. And the second response, which says that there's one single sphere in two different places at once, appears to entail the possibility of an absurd action at a distance. So neither one of those responses work. It appears as if the counterexamples are pretty conclusive. But that's not all. In addition to that, there are
Objections!
Other than the counterexamples, there are two main objections to the identity of indiscernibles. The first, called the objection from near indiscernibles, comes from philosopher Bob Adams, and it goes as follows. First, it is clearly possible for there to be two spheres which are exactly alike in every way except for one. Suppose that they're exactly alike except for that one of them has a slight bump on it. Secondly, it's possible for the sphere that has a bump on it to lose that bump without affecting any other object. If that sphere loses the bump, then you would have two spheres that are exactly similar in every single respect, and yet they are two, not one. It would be absurd to suppose that, as soon as the sphere lost the bump, suddenly one sphere would disappear, and there'd just be one there. That would be absolutely insane. It seems more likely that, if you had two spheres that were almost exactly alike, and then they became exactly alike, you would still have two. The second objection was mentioned by philosopher David Wiggins, and it takes the form of a reductio ad absurdum. That is, an argument which supposes that the identity of indiscernibles is true in order to show that, if it is true, it leads to some absurd and unacceptable consequence. It goes as follows. First, suppose that the identity of indiscernibles is true. Secondly, suppose that there's a sphere made of chemically pure iron that's 1 mile in diameter, that's perfectly spherical, call it A, and also suppose that there's a sphere which is chemically pure iron, 1 mile in diameter, perfectly spherical, and call it sphere B. Thirdly, since the identity of indiscernibles is true, we would have to say that A is B. We have one sphere. Fourth, since this sphere is homogeneous and perfectly spherical, it would follow that its left half resembles its right half exactly. Fifth, but if its left half resembles its right half exactly, we would really have to say that there's just one half sphere, not two half spheres. For the same reason that we would have to say that really there's just one sphere, not two, when we first imagined A and B. But it doesn't stop there, because 6, if indeed we tried to suppose a perfectly homogeneous half sphere, we would end up trying to imagine two quarter spheres that are exactly alike. But, seventhly, if indeed we were trying to imagine two quarter spheres that were exactly alike, and we were supposing the identity of indiscernibles were true, we would have to really say that there's just one quarter sphere, and not two quarter spheres. And it doesn't stop there either. From quarter spheres, we would end up having to go to eighths of spheres, and from eighths of spheres to sixteenths of spheres, and from sixteenths of spheres to 32nds of spheres, and so on and so on. In the end, we would have to say that there's barely anything there at all. Now what Wiggins' objection reveals, in fact, is that if the identity of indiscernibles is true, not only can there be no two objects that are exactly similar, there also can't be any perfectly symmetrical objects. And that's a very surprising consequence, and it's not one that's immediately manifest when you imagine the identity of indiscernibles to be true. When someone says, oh, you can't have two things that are exactly alike in every way, they usually don't intend to imply that you can't have any symmetrical objects either. But, as this objection shows, that's exactly what follows, and that indeed is absurd. Now, in all fairness, Wiggins' objection was, in fact, anticipated by Leibniz himself. In the same letter where he proposes the identity of indiscernibles to Samuel Clarke, he also writes,
Besides, I do not admit in matter parts perfectly solid, or that are the same throughout without any variety or particular motion in their parts, as the pretended atoms are imagined to be. To suppose such bodies is another ill-grounded popular opinion. According to my demonstration, every part of matter is actually subdivided into parts differently moved, and no one of them is perfectly like one another.
So in other words, Leibniz was perfectly aware that the identity of indiscernibles implied that you couldn't have any homogeneous, symmetrical objects. It's just that he really accepted that consequence. He really thought that you couldn't have any symmetrical bodies because of his faith in the idea of a rational God who provides a reason for everything. Today we see that that assumption cannot bear the weight of the counterexamples, nor can it bear the weight of the other objections. It seems pretty clear, in other words, that, in addition to counterexamples, these two objections show that the identity of indiscernibles is probably completely false. So that's pretty much it for our discussion of whether the identity of indiscernibles is true. It looks like it's completely wrong once you think about it. However, there are still many other exciting questions left for us to explore, including, what is a thing, anyway? Is a thing anything more than just a collection of features? Is there something extra to a thing besides its properties? And speaking of properties, what are those? Are they things at all? Well, we'll get to those questions in due time. But, for now, thanks for watching.